Hello and welcome to Controllers Tech. Before we begin, I would like to give a big thank you to our Patreon members, David Lutz, Friedrich Boak, and Robert Johnson, for their generous support. Today, we are starting the Modbus TCP series. In this series, we will see how an STM32 can act as a Modbus server, also called a slave, which responds to queries from a client. Later in the series, we will also make the STM32 act as a Modbus client, which will connect to another server and request data from it. In this first video of the Modbus TCP series, we will see how to configure the STM32 as a Modbus server, and how the Modbus master can read discrete inputs connected to this server. I will use an application on the computer to act as the client, or master, which will connect to the server running on the STM32. The client will then request data about the discrete inputs connected to the server. For this entire series, I will be using the Mongoose networking library. Mongoose is an open-source networking library designed for embedded systems and IoT devices. It is written in C and is very lightweight, which makes it a perfect fit for microcontrollers like the STM32 where memory is limited. What makes Mongoose really useful is that it supports a wide range of network protocols, including HTTP, HTTPS, WebSocket, MQTT, and of course, Modbus TCP. It handles all the low-level networking details in the background, so you can focus on writing your actual application logic, instead of dealing with complex networking code. Mongoose is also trusted by some big names in the industry. Companies like Siemens, Texas Instruments, Renesas, and Bosch have used Mongoose in their products, which speaks a lot about how reliable and production-ready this library is. For this series, Mongoose is the perfect choice, because it gives us a simple and clean way to set up a Modbus server on the STM32, without writing everything from scratch. Now that we understand what Mongoose is and why we are using it for this series, let's go to the Web UI wizard to create our project. Click on New to create a new project. First, let's select a directory where we will store the project. I will create a folder specifically for all slave-related projects. We will keep coming back to this project throughout the series, and add new features to it over time. Next, we need to select the target hardware. Mongoose supports almost all official STM32 development boards that have an Ethernet PHY on board. I am using the STM32 Nucleo H755ZI, and I will be using it for the entire series. After selecting the board, we need to choose the IDE. Here, we will use STM32 Cube IDE. We are not using an RTOS, so select bare metal. Now we need to select a starting dashboard. Let's pick the LED toggle option, as it is the simplest default dashboard to start with. Next, go to the settings page and make sure to enable the Modbus TCP server option. Leave the server port set to 502, as we saw in the previous video. 502 is the standard port for Modbus communication. That is all we need to configure in the wizard. Mongoose will automatically generate all the initialization and pin configuration code for the selected board. Click Generate Project to generate it. As you can see, the entire project has been generated inside the selected directory. There is the Cube IOC file, which we will modify shortly to add our inputs. There is also a separate Mongoose folder that contains all the Mongoose-related files. This folder gets overwritten every time you generate the project from the wizard again, so make sure you do not write or modify any of your own code inside this folder. Now, let's open STM32 Cube IDE and STM32 Cube MX. We will first import the generated project into STM32 Cube IDE. Browse to the project folder and click Finish to import it. Since the Nucleo H755ZI is a dual-core board, both projects, one for each core, will be loaded into the IDE. I will only be working with the Cortex M7 core, so let's open the main file of CM7 project. You will notice that the code has been generated to initialize the second core as well, but since we are not using it, I will comment out all the code related to the second core. That is all we need to do here for now. Let's build the project. The build completes with no errors. Now let's open the Mongoose folder, and then open the Mongoose configuration file. I have already explained this configuration file in detail in my previous Mongoose videos, so if you want to understand how it works, you can check those out using the link in the top right corner. Since I am connecting the Ethernet cable directly to the computer, I need to use a static IP address. By default, Mongoose is configured to use DHCP, but there are some definitions in the configuration file that we need to uncomment in order to switch to a static IP. You can set the IP address based on your computer's network settings. For example, my Ethernet configuration uses the same gateway that is already set in Mongoose, so I will leave the default values as they are. This IP address will be the server's IP, which we will enter into the client later. Let's build the project and do a quick test to make sure everything is working so far. Open the serial console to view the logs. You can see that the log shows the network is down because Ethernet is not enabled yet. Once I enable it, the IP address gets printed on the serial console. If you are using DHCP, you will need to check the logs to find the IP address assigned to the STM32. But even with a static IP, it is always a good idea to check the logs to confirm everything is working correctly. Now if we browse to this IP address in a browser, you can see the default web UI panel has loaded. We are not going to use it for now, but it is there by default. Now let's open the mongoose glue.c file. This is the file where all the working functions are generated by the wizard. We need to work with these functions, and any new functions created from changes made in the web UI will also be placed here. For example, since we enabled the Modbus server, you can see that a Modbus handler function has been generated here. We need to use this function to handle Modbus requests coming from the client. However, as I mentioned earlier, we should not modify the code directly in this file, because if we regenerate the project from the web UI wizard, everything here will be overwritten. So instead, we will copy this entire function and paste it into our main file, where we will make all our changes. If you look at this function, the logic is straightforward. It first checks whether the client is requesting to read coils or to write coils, and then performs the matching operation. Since we are not doing any writing in this video, I will remove the write section from the function. We are also not reading coils, we are going to read discrete inputs. So we need to find the correct function code definition for that. Here you can see different definitions based on Modbus function codes. We need the one for reading discrete inputs, so let's copy it and place it inside our Modbus handler. This means that whenever the client requests to read discrete inputs, we will handle it here. We will complete this function in a moment. But first, let's understand how the inputs are physically connected to the STM32. Here is a diagram showing how I have connected 10 different inputs to different pins of the STM32 Nucleo board. Each input is connected to ground through a switch. When a switch is closed, that input reads 0. When the switch is open, the pin is pulled high to VDD, so the input reads 1. This gives us 10 individual inputs that we can control independently. Now we need to configure these pins in CubeMX. So let's open the CubeMX, and load the project into it. Alright, the project is loaded. Let's start with the first input, which is connected to pin PA3. Set it as a GPIO input and make sure it is assigned to the Cortex M7 core. Since this is a dual-core board, this step is important to ensure the pin is controlled by the correct core. Now rename this pin to input 1. The next input is PC0. Set it as a GPIO input, and name it input 2. Then we have PC3, which will be input 3. You can verify all the pin connections using the Nucleo H755ZI schematic. I have gone ahead and configured all 10 pins as inputs, and renamed them according to their number, so they will be easier to work with in the code. Now go to System Core, GPIO, and set all the input pins to pull-up mode. This means by default each pin will read high, that is 1, and when its switch is turned on, it will read 0. That is all we need to configure in CubeMX. Click Generate Code to generate the project, and click Yes, if it throws the error about the assignment of the rest of the pins. The project has been generated, so let's go back to the IDE. I am going to define a structure with 2 elements, one for the GPIO port and one for the GPIO pin. This structure will represent a single input. Then I will create an array of this structure called inputs, and populate it with the port and pin combinations for all 10 inputs. You can see that we are using the pin and port names that we defined earlier in CubeMX, such as input 1 GPIO port and input 1 pin. CubeMX automatically generates these definitions based on the labels we gave to each pin, which is exactly why we renamed them. It makes the code much cleaner and easier to read. So now we have a simple array where each element holds the port and pin information for one input, and we can access any input just by using its index number. Next, I will write a new function to read the inputs. This function takes a single parameter, the input number that the client wants to read. If you look at the Modbus handler function, you can see that the read coil function is called once for every coil the client requests. We will use the same logic here. Our read input function will be called once for each input, and the parameter carries the input number the client wants to read, which starts from 0. Inside this function, we simply call HAL GPIO read pin, to read the state of the respective pin and return the result. If the pin is high, the function returns 1, and that value gets passed back to the Modbus handler. Similarly, if the pin is low, a value 0 will get passed to the Modbus handler function. Now let's build the project. We have an error, and that is because our Modbus handler function has the same name as the one already defined in the Mongoose glue.c file. To fix this, we just need to rename our function. I will call it my Modbus handler. However, renaming it means the Mongoose library will not automatically recognize it, since it is set up to look for the original glue function. To solve this, after Mongoose is initialized in the main function, we call Mongoose setModbusHandler, and pass our function as the parameter. This registers our function as the official Modbus handler that the Mongoose library will use. With that done, there are no more errors. Let's flash the project to the board. After resetting the board, you can see in the serial console that the server has started and the IP address is printed. Now let's configure the client. I am using an application called simply Modbus TCP Client on Windows. Since this application is not available on Mac, I am running it inside a virtual machine. This software will act as our Modbus TCP client, sending requests to the Modbus server running on the STM32, and receiving the responses back from it. At the top, select the TCP mode, then enter the server IP address and port. Next, click Connect to connect to the server. As I mentioned in the previous video, the slave ID does not really matter when you are connecting to a single server, but we still need to enter a value, so I entered 10. Since we want to read discrete inputs, the function code will be 2. The starting address for discrete inputs is 1001, so enter that in the address field. The offset should match, so that the address is correctly mapped back to 0 on the server side. We want to read 10 inputs starting from the first one, so set the quantity to 10. Now click Send to send the request to the server. We have received a response from the server, and you can see all the values are 0. On the left, you can see how I have connected the inputs on the STM32 Nucleo board. I do not have 10 physical switches, so I am using simple wire connectors to connect the input pins to ground. Right now all the connectors are connected, which is why all inputs are reading 0. Now let's take a moment to understand the raw data exchanged between the client and the server. The client sent the following: first, 2 bytes for the transaction identifier, which is 00 followed by 01, this is a unique ID generated for each transaction. Next, 2 bytes of protocol identifier, that is 00 followed by 00, which is a fixed value used in all Modbus TCP messages. After that, 2 bytes indicating the length of the remaining data, which is 6 bytes. These 6 bytes include 1 byte for the slave ID, 1 byte for the function code which is 2 bytes for the starting input address which is 0, and 2 bytes for the number of inputs to read which is 10. The server responded in a similar format. It sends the same transaction identifier, followed by the protocol identifier, and then the length field which is 5 bytes. Those 5 bytes include 1 byte for the slave ID, 1 byte for the function code, 1 byte indicating the actual data length which is 2 bytes, and finally those 2 bytes are the actual input data, which is all zeros at this point. Now I am going to disconnect the common ground connector. With nothing connected to ground, all pins are pulled high to VDD through the pull-up resistors. If we send the read request again, you can see we receive all ones, 8 ones in the first byte, and 2 ones in the second byte, giving us a total of 10 inputs all reading 1. Now let me change only a few inputs. I will leave inputs 2, 5, 7, and 10 disconnected from ground, so those should read 1, while the rest remain connected and should read 0. The expected result is 0100101001. Let's send the request and see what we get. As you can see, the response matches exactly what we configured on the STM32. Let me make one more change. This time I will connect all inputs to ground except input 2, which stays open. Sending the request from the client gives us exactly that result, only input 2 reads 1, and the rest are 0. So, the communication is working perfectly. The STM32 Modbus server is correctly responding to requests from the client and accurately reporting the real-time state of all 10 inputs. Now let's make things a little more interesting by using the web UI to visualize the real-time state of the inputs. Let's go back to the dashboard. First, we will make some changes to the default LED container. Rename it to Discrete Inputs and delete the second LED element, we only need one for now. Rename the LED label to this template string, where I is a variable that starts from 0. By adding 1 to it inside the template string, the inputs will be displayed as input 1, input 2, input 3, and so on. You will notice an error at this point, that will be resolved shortly. Now go to the REST API section and delete the default LED endpoint. Create a new endpoint and name it Inputs. Set the endpoint type to Array, so that all 10 inputs can be handled through a single endpoint. This endpoint will have one attribute of type Boolean, which will indicate whether each pin is high or low. Since discrete inputs are hardware-based and cannot be changed from software, we will set this endpoint to read-only. This means the web UI will only display the state of the inputs, and will not allow any modification. Go back to the page content section. The toggle button will use the endpoint we just created. Make sure to pass the array element reference so that each generated element shows a different value. Then click on the container and pass the Inputs API variable. You will see that all the errors are now automatically resolved, and the label shows input 1. As more elements are generated in the array, this container will automatically expand to display all of them. Now go to Settings and enable WebSocket. Since we need to read the state of the inputs frequently and keep the UI updated in real time, WebSocket is the right tool for that job. That is all the changes we need to make in the wizard. Click Generate Code to regenerate the project. This will only overwrite the Mongoose related files, it will not touch any of the changes we made in the STM32 project, so our CubeMX configuration is still safe and does not need to be redone. Now in the Mongoose glue.c file, you can see that new functions have been generated. There is a structure for the inputs, along with a getter and a setter function. The getter function is called by the web UI to read the current state of the inputs, while the setter function is used to change them. Since we are working with read-only hardware inputs, we only need the getter function. Let's copy it and paste it into our main file where we will modify it. The first thing we need to do is increase the number of elements in the inputs structure array from the default to 10, since we have 10 inputs. Also, rename this array to something different, because the original name is already used in the Mongoose glue.c file, and will cause a conflict. For the same reason, we also need to rename the getter function, since glue getInputs is already defined in the glue file. Now let's understand what this function does. First, it calculates the array size requested by the web UI. Then it performs a size check, and after that it copies the data from the inputs array into the structure that gets sent to the web UI. To feed the real-time state of our physical inputs into this structure, we need to update the inputs array before the data is copied. Right after the size check, we will add a for loop that reads the current value of each input using our readInputs function, and stores it into the discrete inputs array. We are reusing the readInputs function here because it keeps the code clean and consistent. Our getter function is now ready. However, just like we did with the Modbus handler, we need to register it so that Mongoose recognizes it. We do this by calling Mongoose setHTTP handler and passing 3 parameters. First, the name of the API variable exactly as we defined it in the REST API section of the wizard. Second, our custom getter function. And third, the setter function. Since we do not have one, we just pass null here. The last step is to set up the WebSocket reporter, so that the web UI receives regular updates. Mongoose has a dedicated function for this called Mongoose add WS reporter. The first parameter is the update interval in milliseconds, the default is 200 milliseconds, which is fine for our use case, so we will leave it as is. The second parameter is the API variable we want to update, which in our case is inputs. That is all the changes we need to make. Let's build and flash the project to the board. Now let's open the server IP address in a browser. You can see that all 10 inputs are listed here, since we defined 10 elements in the inputs array. Each input is displaying its current real-time state. Right now, all the wires are connected, so all inputs are reading 0. If I remove the first wire, you can see input 1 immediately switches to 1. Let me also remove the wire for input 5, that also switches to 1. And now input 9, same result. So with 3 wires removed, those 3 inputs are showing 1 on the web UI while the rest remain 0. Now if we go to the Modbus client and send a read request, you can see the data returned is exactly the same as what is being displayed on the web UI. This confirms that both the Modbus client and the web UI are reading from the same source, the actual hardware inputs on the STM32. The web UI here is simply a visual display of the current state of the inputs. Since discrete inputs are hardware-based and cannot be controlled from software, I have not added any control functionality for them on the web UI. However, we will implement that in the next video when we work with coils, since coils are output devices that can be both read and written. So, we saw how to configure the STM32 as a Modbus server, and how a Modbus client can read discrete inputs over Modbus TCP. We also saw how to use the Mongoose web UI to display the real-time state of those inputs. In the next video, we will continue with the STM32 as the Modbus server, but this time we will see how the client can read and write coils. Coils are single-bit output devices, and we will connect LEDs to the STM32 to physically see the client controlling those outputs. That is it for this video. I hope everything was explained clearly. If you have any questions, feel free to leave a comment below. You can download the project from the article linked in the description of this video. Keep watching and have a great day.